worry, you need to allow me to share my screen.
Can you try now?
Yeah, perfect. Okay. Okay, so we had already gone there. Okay, now 4 by 7. So 7 parts and 4 of that. So that's 4 by 7, which is now getting. So we got 2/3 of 4 by 7. Okay. So we can see both the products on either side. Now let's take a look at this. So this is 2/3 times 4 by 7. Let's focus on just the shaded portion. Rotate. Now extend the whole. Okay. And now after rotation, it is actually 4 by 7 times 2/3. So same idea of rotation, okay, but it gets a bit nuanced here because of the hole. Okay, so there we go. Now with multiplication with negative numbers, now we kind of do something different. What we will do is, we will first establish this positive negative combinations, okay, and then we are going to use proof, no visualization, etc. The visualization will be just to get those positive negative aspects, and then it will be proof. Okay, so you have already seen this. So that's 4 times negative 3. Okay, and note that it is just a mirror reflection of 4 times 3. So 4 times, so there is reflective symmetry. You can see these two triangles that are formed by this slant line, the light blue number line, and the darker blue vertical number line. And you can see these two triangles kind of are mirror reflections of each other. So this 4 times negative 3 is nothing but negative of 4 times 3. That is, their magnitudes are the same for both the products, and they just have different sign. Okay, and again this can be generalized, right, not only for any integers but for any rational and uh, real numbers. Okay, uh, so now negative times positive, so that's negative 4 times 3. Okay, and if you stretch it up, you can see that again you can see two right triangles, and they are kind of rotational. You rotate one by 180 degree and you get the other. Okay, so it's also a case of point reflection. They have been reflected at the origin, so to speak, right? So again, negative 4 times 3 is nothing but negative of 4 times 3. Same magnitude away from 0, but on opposite sides of 0. Okay. As usual, generalizable. Instead of 4 and 3, it could be any two real numbers. Positive real numbers or positive rational numbers. I mean, A and B we are taking as positive. Okay. So now what happens to negative times negative? Okay. So negative 4 times negative 3. Okay. And that's 4 times 3. Now this is again a reflective symmetry, if you can see. But this time it has been reflected along the x-axis. In the first case, it was reflection along the y-axis, but this time it's a reflection along the x-axis. X-axis is not shown here, by the way. Okay, but you can imagine that that line. So in this case, not only is the magnitude of these two products same, but they are also on the same side of 0. So negative 4 times negative 3 is the same as 4 times 3. Okay. And as the other two, this is also generalizable. Now, so for rational and real numbers, also you will get the same thing. Okay. I don't know. Okay. So for the integers, we get this. Okay, I'm not sure why that heading is saying that. I definitely need to look at this PPT again. Yeah. So similar result can be obtained for rational numbers on a larger grid. You need to use a chart paper or something, or uh, a graph sheet will be able to give you something, not all possible, uh, not a whole lot of denominators, but you can deal with it with decimals to an extent. And when it comes to real numbers, that's where the GeoGebra thing is important. Okay. So these are three results which we are going to use. These are three results we have established. Okay. So when it is whole numbers, we will use, for integers, we will use M and A. For rational and real numbers, we will use A and B. That's it. Okay. Um, for integers, these three things can also be established by extending the tables, and that is done beautifully in the NCRT textbook class 7 integer chapters. Okay. And that can be, that extension of tables works because again of the discreteness. But when it comes to reals and rationals, I don't know how to get the similar results except for this model. Okay. That's why, I feel it is important. Okay. Now let's get to the proof. Okay. So these are established results. Okay. And we already know that m times n is equal to n times n. Okay. We have already established that. So, if you have uh, positive, negative, then you can get the first line by 1, and then using the commutativity of the whole numbers, you get the second one. Then you again apply 2 to get the last line, and you notice that now we have established commutativity. It's a very short 3-step proof. Okay. And it's logically establishing it. Now, if you have negative times negative, so you use 3 to get that it's this. Then by 4, by using the commutativity of whole numbers, you switch them. And then you again apply 3, and you are done. Okay. So not very complicated, but this way, you are pushing the children to abstract out a little bit, get a flavor of, logical arguments which are based on one another. Okay. Usually that's how geometric theorems go. But I mean, the theorems in geometry go, but in numbers also you can give them a flavor of that, this whole logical argument kind of a thing. Okay. Uh, so for commutative property of multiplication for rationals and real numbers, it's identical. Okay. So here A, B are, I should not say fraction because that will not include things like pi. So yes, that's another thing that needs to be changed. For any A, B positive, that's what the first line should say. You again have these results which you get from similar exercise on GeoGebra. Um, and you have already, yes, okay. So for fractions and for reals, and you have established A times B equal to B times A for fractions. fractions, and you can establish the same thing for real AB, again by rotating. Okay. um, and then the proof is exactly along the same line. You just replace the m, all the wherever you see m, you replace it by a. Wherever you see b, you replace it by, wherever you see n, you replace it by b, and that's it. Okay. So the only difference is in establishing these three results and this result. For fractions it is easier to establish. Okay, you can actually draw pictures if necessary. uh, but when it comes to reals, uh, for fractions this we have actually established very uh, significantly. For reals, this comes from GeoGebra. For reals, getting this is, it requires a bit of, I would say, a leap of faith to an extent. There you have to kind of um, think about this whole area aspect as, area of a rectangle with sides A and B as A times B. You can't directly show it for reals. You can show it up to fractions. Okay. But you can't directly show it for reals. What you can think of is a decimal approximation kind of a thing. Okay. I mean, any decimal approximation is essentially a fraction. So all the decimal approximation will work, and they will, you know, you can, it will either grow to, when you approximate from the, yeah, when you approximate it, it will basically, the limiting case will be for reals. Now there is a question here, why do we even need this? You need this because you are going to multiply stuff with pi, if not anything else. And as I already said, pi is very irrational. Okay. So that is why this is kind of important in my opinion, but this is where we kind of take a leap of faith. Most of us do. Okay. Um, yeah. The rest, as I said, now associative property of multiplication again can be proved in a similar line, and whatever happens for uh, integers will again happen for real numbers and rational numbers in a similar way. But let's get started with the whole numbers first. Okay. So there are several plates and there are some blocks, and each block is made up of certain numbers. So there are two ways we can count it: number of plates, number of blocks, and number of squares in each block. That's the basic idea. So one way of counting is how many squares are there in each plate. Okay. And then how many plates. Okay. So that's one way of counting it. The other way of counting would be, so this is the first way of counting: number of plates times number of squares in each plate. And that gives us one expression. Another way of counting will be how many blocks in all plates. Okay. And then how many squares in all plates will be this, how many blocks times how many squares in each block. Okay. So one is counting plate wise, another is counting block wise, and that generates these two different expressions which are slightly different, but we are essentially counting the same thing. Okay. um, this however cannot be extended to fractions. So but what we do for fractions can be extended to real numbers, and I've seen that in some book or some article. Okay. uh, But this is something that I found probably a bit better to start off, um, just a quick note: this commutativity of multiplication and later distributivity, and this associativity, especially the associativity part, I learned from Padmapriya Shirali in her multiplication pullout. Okay, that's one of my most favorite pullouts because it basically planted the seeds to explore what I'm describing to you in the first place. I mean, commutativity, distributive was okay, understood, etc. Associativity was something that which generated a big aha moment, and also, where we actually use the associative property without realizing we do that. So, and that's what triggered this whole exploration into, okay, so try to explore all these 5 properties for all the different number sets. Okay, so just wanted to acknowledge her. And the work is not done yet. Reals and rationals are painful. Okay, so for, and this is quite complicated, so let's just look at it. So if you have A, B, C, 3 things are getting multiplied. So A is shown around the y-axis, B is shown along the x-axis, and C is shown along the z-axis. That's the height. This is for you to understand. You don't have to use the same language with children. Okay, just to make you uh, uh, help you understand. So A times B is the shaded area of the horizontal cross section, right, along the xy plane. And B times C is the shaded area of the vertical cross section along xz plane. Okay, so it's all going to make sense as we go into the pictures. So these are one of the most complicated pictures I've ever drawn. So that's, again, 4 by 3 is a improper fraction, right? So you need two wholes. And because we have 3 fractions, we are using getting to the 3 dimension. Okay. And therefore, we have to use the unit cube. We had used square so far, but here we have no choice but to get to the unit cube. I don't know how to create a model of this, but what you can do is, there is something called isometric sketches that is there in the syllabus, at least for CBSE, in class 7, etc. And so when you teach that, you can use that on triangular dot sheets to draw these kind of things. There you need to choose your denominators carefully. So for example, if you choose a denominator of 6, then you can have 3 fractions with denominators, let's say 2, 3, and 6. Okay, and you can show them, do these things that way. Okay, or so that way, it can be drawn on dot sheets, the same thing. Okay. And here, I have taken the trouble to ensure that at least one of the 3 fraction is improper. Um, to start with, you can take only proper fractions, which will be more manageable. You are confined to only 1 cube. And then you can try to think about, how to represent the whole thing in for if you have one improper fraction or more, etc. So those are things for you to explore. And as usual, if you consider the combinations of proper improper, 2 to the power 3, so 8 possibilities, right? So I'm just doing a slightly difficult version. Okay. Okay, so the second fraction is 5/9. So this whole thing is getting split in, 9 parts, and 5 of them are reserved. Okay, so 5 of the, so this is 5/9 of 4/3. Now we have it. Okay, so that's the left hand side. Okay, now the RHS. So we start with 5/9. Okay, and then we have it. And now we take 4/3 of this. So that's 3/3. So we need another 1/3. Okay, so this is the RHS. And you can see that they basically represent the same volume. So they are equal. Okay. Now, uh, so again, generalizable for any three fractions, so to speak. This thing, this model can be used for whole numbers with unit cubes. Okay, and I've seen that to be done. But I like those plates and bundles idea a lot. More, it's easier to do. Okay. So associative property of multiplication. Again, proofs using similar ideas. So the same results that you have, except for the fourth one, which is now the associative property for whole numbers. Okay. First three are identical to the previous one. So as you can see, tons of possibilities considering the positive negative combination, right? In fact, total 8 possibilities, and if you include the all positive combination also. So the ones in blue are the ones which is shown. You can try the others on your own. It will be very similar. Okay. So, so this is by 1, where you have positive times negative becomes negative of a product. Then negative times positive becomes negative of a product. Now you use the associative property. Then you use 1 reverse way, and then you use 2 reverse way, and you realize, okay, we have got what we wanted. Okay, so it's not very tough, but it's systematic, logical, rigorous, and it's good to give students a taste of that. Not all will appreciate it, but what, there's hardly anything in the world which is appreciated by all. So the other one is can be shown in the similar way. These two, okay, very, very similar. So now let's look at positive times times negative. Okay, so 2 negatives. So first you get the same, first step is very similar. Then you use 3, right? Now you have two negatives. Associativity, reverse application of 3, and that's it, right? So if you have 2 negatives, it became actually shorter. Okay, so anytime you have 2 negatives, it will be a shorter proof probably. Okay, all negative. Okay, so application of 3, application of 1, associativity, application of 2, and application of 3 again. Okay, this is going to be identical. Okay, so same 3 as before, and associativity for fractions again establishing for real has, you have to do it as a volume, and it has the same issues that you have for the area thing also. Okay, it is, you do take a leap of faith to an extent, and the proofs are exactly the same. So replace all the m by a, all the n by b, all the p by c. That's it. Okay. Now, after doing this much work, when it came to distributive property of multiplication, whole numbers is easy. So, and this is used a lot. Anytime you are doing multi-digit multiplication, at the heart of it is this. Okay. So, use counters, doesn't have to be in so many colors, etc. That's, just exploiting technology, so to speak. So that's it. There should have been another round of it. Okay, so not completely happy about that. Yeah. Anyway, you'll see what I mean very soon. Okay. So 3/4 times 4/7. Okay. Now 3/4 times 2/3, and you add them. On the other hand, this is 4/7, and this is 2/3. So the total shaded area is 4/7 plus 2/3. Okay, and we are going to take 2/3, 3/4 of that. Okay, now this is identical to the picture we had generated earlier, so both are equal. Okay, very similar concept, and you can see the use of array. It's an extension of what you saw for whole numbers. Now, integers. This is where the array with the flip is used, just like it was used in commutativity. Okay, you can't use the array to establish that negative m times n equal to negative m times n. That you can't. But once you have established those three relations in terms of multiplying with negative numbers, then you can use the array with the flip. Flip meaning changing signs. The reason I'm using the flip is because if you use counters which are double-sided, then you just flip them over. And if you flip them twice, you get back to the original. So flip kind of works very nicely. Along with negative times negative is positive. So it's good to have double-sided stuff. And I ran into double-sided stuff as an accident. In mathematics, math pedagogy, some accidents are often good. So if you can learn to identify the good experience, good ones, makes it your life more, it makes your life richer. Okay, so 4 times -2 and 4 times 5. So you combine them, remove 0 pairs, that's what you are left with. Okay, that's the sum of the two products. This is what I'm showing in this slide is missing from the whole number slide, and that needs to be added. Okay, so I've got 4, I have got -2 plus 5, and I'll remove the reoperas now. That's what is left. So this is identical to what we had. So what is happening here is when we are showing it as a sum of products, you get the two arrays and you add them. But when you want it to show as a product where one of the factor is a sum, you take care of that factor, that border of that array first, and then create the array. Okay, that's how the two are different. Okay, so this is one with uh, it's just the common side is negative, so very similar. So you can see that here negative times negative is positive has been used. Negative times positive equal to negative has been used. So those three results has been used to choose the color of counters you use to fill the array. Okay, so this is where the array with flip comes in. And you remove zero pairs, so this is the resulting array. Okay, and now so we set the borders and we remove the zero pairs from the borders before getting into the array. Okay, and the two are identical. Now this is where I had hit a big roadblock, because um, when we were dealing with the multiplication, the commutative and associative properties, it was just multiplication. So proof worked, right? But here addition also comes in, and I was literally clueless on how to, combine the, do it only through proof. Maybe it can be done, but frankly, I don't know how to do it yet. Okay, so proof was out, and I couldn't use the array in the same way because rational and real numbers don't have discreteness. So I was really stuck here for some time, and then I thought, well, the only way to generalize will be, the way you generalize to length there, same way here you generalize to area, and that kind of paved the way. So, okay, so you get the lengths, and then correspondingly you get the area, which represents a times b, and similarly you get the other area. Again, you see this is now signed area. You are again using those, that uh, positive times negative generates a negative number, that aspect you are using here. So now you have got the products, the two areas, and like we removed zero pair there for integers, here we remove equal areas. Okay, or remove zero area. Okay, so this is the resulting array, the uh, resulting sum. Now if you want to do the other way, you get the borders and you remove the zero length here, just like we used removed zero pair. Okay, and now you generate the resulting array, and which is identical to what we had got before. So this is the other one with, yeah, so the positive negativity of A and C, okay, so both negative, B and, okay, so both areas are negative, so there is no question of removing any zero pair here, a zero area here, so the whole thing is that. Okay, and similarly, since the whole border is negative, there's nothing to remove as such. So together it is negative b plus negative c, and that's the resulting array. Okay. Now, obviously for integers there will be a version of it. I have not shown you all possible positive negative combinations. Um, and this is where you have where the first number is negative. Okay, so same idea. You can see the flipped array and stuff. Also notice that here I have violated my own convention of having the first number as the vertical dimension. That does need to be fixed. So since it is more trouble to change the picture, I'm going to change the text. So that also needs to be done. So once I make all these basic changes, I'll share this PPT with you. Okay. Um, so that's all for the properties aspect. Okay. Um, any question? Did you get a sense of how these are different from case by case checking? There you pick 2 numbers or 3 numbers, check, compute left hand side and compute right hand side. Was that part clear? Thanks, Ranjit. I mean, you can use the chat to respond also. Uh, so now I have a question for you. Um, and that is, uh, did you get a chance to look into the countable, uncountable stuff that I had sent? Okay. Now, I don't know if anybody other than Ranjit is awake or not, or is listening or not. So, need some response from you. Shiva, I saw you unmute, but I couldn't hear anything.
No, Swati, I didn't read that part.
Louder, please.
No, I didn't read.
Okay, that's fine. So, please